In this lesson, we will do the complexity analysis of a hash table. So first, let's look at the space complexity. So if we are storing m keys, then the space complexity will be O of m. So if we are storing m keys, then we will have some table and there will be some buckets within that table, and we will have maybe multiple keys in some bucket. Some buckets may be empty, some bucket may have 2 keys, some may have 1 key. So in total these all sum to m. So we are storing some fixed number of buckets and overall m keys. So O of m, assuming that the number of keys is large compared to bucket, or if we are having a predefined bucket size and b is of the order of m, then we can also write O of b. But at least we are storing m keys, so at least we need m spaces. Some buckets may be empty, so that will add to extra space. So we can write O of m plus b, or whichever is larger, you can assume that. Now let's understand the more critical part, that is time complexity analysis. And we are mainly talking about insert and search operations, because we will insert keys into the hash table and then later we will search it, and we can also remove from the hash table. So remove will be just extension of insert, where extension of search, where we will first find the key, search it, and then get rid of that. So it will depend on design, how you design the hash table. So for example, you have a predefined table size and it will have different buckets. Now within the bucket, let's say you are storing the keys sequentially, maybe in a linked list or in an array. So if on average these bucket sizes are small, then calculating the hash code, so you will have some data. You will first need to convert that to 0 to bucket size -1 value, map that to here, and then within that bucket you will search the key. So if the number of elements in each bucket is low or some constant, then even searching in this linear storage will take O of c time, that is O of 1 if c is small. So that will be the search operation. Similarly, if we are doing insert, you will just calculate the hash code. You will go to that bucket and you will insert the element in the end. So both insert and search and delete will take O of 1 time if number of keys in each bucket is small. But what happens if the number of keys is large? So if it's some value, let's say n, where n is not a small constant, then again insertion you can do it in the end. So insert will be O of 1. So this was for the case of c keys in each bucket, and here it's n. But search in a linear array or linked list, it will take O of n time. So what you should do in such cases, you should not use a linear storage like array or linked list for storing your keys within the same bucket. So in such case you may use, let's say, a balanced binary search tree. So in that case you will store, so keep in mind that these all keys are within the same bucket. We are talking about within a bucket. So again insertion and search both will take log of n time in this case. because even if you have to insert, it's a balanced binary search tree, so you have to maintain the search property. So in the worst case, it will take log n time. You may have to go all the way to the bottom level, that is log nth level, and insert the key there. And similarly, search will take O of log n in the worst case. So in this case, we have improved the search time from on to O of log n, but we have deteriorated on the insert timing. So there has to be a trade-off between these two. Depending on your use case, you may have to do very less searches, or let's say you have you insert very less frequently. That is, you have a huge data, you have already inserted it, and it changes very less frequently. So your main operation is search. So you try to optimize search. But let's say you have too many insertions and deletions, then you have to optimize insert also. So this was a general time complexity and a space complexity analysis for hash tables. I hope you find this lecture useful. So see you in the next lesson.